classic children's toy in the United States. You've probably played with one, or at least heard of it. Slinkies are just long springs. Their large size and low spring constant allow them to do some interesting things. For example, they walk downstairs, and they're just generally captivating. But one of the most interesting and exciting aspects of a Slinky can only be seen when it's dropped. When I slow down the video, it's pretty easy to see some interesting behavior. I drop the top of the Slinky, and the bottom doesn't begin to move until a short time passes. Why does that happen? To further investigate the behavior of the system, we have to come up with a model for a spring. The way that we do this is by modeling the spring as a series of points, a series of masses, each connected by a spring.
We call the resting length of this spring 2 times the radius of each individual mass. This means that when the 2 masses are touching, the spring won't have any effect on the 2.
When a Slinky is at rest, it's collapsed. All of the rings are touching each other. We need to set up the initial conditions for before the Slinky falls, before I drop it. It's apparent that before I drop the Slinky, it isn't uniformly stretched out. The part at the top is significantly more stretched out than the part at the bottom. Our next task is to find the initial conditions of the system before the fall. The force diagram on the left is what allowed me to create the equations on the right. These are the equations for motion of the system at any given time. Before we start to explain the falling motion of the Slinky, let's watch it again. Notice how as it falls, each ring runs into the next. It doesn't rebound, and it doesn't go through. The 2 collide and stick together. An inelastic collision is occurring. Now, you may not have noticed that velocity decrease, and that's all right because it isn't actually visible to the eye when we watch the Slinky fall. This is because an actual Slinky is made up of an infinite series of points, and they are continually colliding into one another. This continuity of collisions means that there's no point when the velocity suddenly plummets. All of that is well and good, but we still haven't answered the big question. Why in the world doesn't the bottom of the Slinky move as soon as the top is released? I made a VPython program so we can model the system in order to observe its behavior. The system finds its equilibrium position, and then it falls. We can look at the inelastic collisions by watching the velocity of the first mass versus time. It will be involved in every single collision, either directly or indirectly as part of the whole conglomeration of masses. The first peak occurs when that first mass hits the second mass. The inelastic collision occurs, and their combined velocity is suddenly lower than the first mass's original velocity. Those 2 masses hit the third mass, and their velocity again decreases. This process continues until all of the masses have been hit, and the conglomeration just begins to fall. That's what the final increase is to the right of the screen, when the masses are all stuck together and falling. Notice that the bottom mass is still stationary. It hasn't moved yet. The acceleration seems to remain 0 for a finite amount of time after the top mass is released. Let's watch that again in real speed. So we can see that the acceleration of the bottom mass is equal to 0 for a finite amount of time after the release of the top mass. We take this acceleration and plug it into the equation F equals ma and conclude that the sum of all the forces on the bottom mass is equal to 0 for a finite amount of time. The motion of the top mass at its release changes the distance in between it and the second mass, which changes the spring force in between the two. This change in the spring force causes the second mass to move, which in turn changes the distance between the second and third mass. This pattern continues on until the final mass is reached and the bottom finally begins to change position. So, the bottom of the slinky seems to stay suspended in midair because the forces cancel out for a finite amount of time after the top is released. We've answered our question! Yeah! But wait, is that more physics calling? I believe it is. My slinky's pretty small. What if we had a whole plethora of slinkies of all different sizes? What then? The bottom of my slinky starts to fall at a certain time after I release the top. Would all the other slinkies be the same? Would it take the same amount of time for their bottoms to start falling? How much time will elapse between the time that we release the first mass and the time when the bottom mass, here, begins to fall? We want to investigate the relationship between time elapsed and mass of the spring segments. I run the program repeatedly, changing the mass of each point as we go. I then record the time at which my final mass begins to fall. Here's my original data, and here's its graph. We can see that it looks very logarithmic. Plotting the log of the mass against the log of the time reveals a set of data that looks incredibly linear. This is the line that is revealed by the linear fit, and its parameters are on the side. M is the slope of the line, and it's about 0.48. Let's look at this number, investigate it a little bit further. Let's think about how we would expect the time to relate to the mass. Dimensional analysis gives us a time that is proportional to the square root of m over k times some constant c. When we take the log of both sides, we end up with this equation. We compare this equation to our linear fit equation. Log of t is comparable to y, log of m is comparable to x, and negative 1/2 log of k plus log of c is comparable to our constant b. From dimensional analysis alone, we would expect the log of t to relate to the log of m through a factor of 1/2, and this is indeed what we see when we look at our data. We notice that the uncertainty doesn't quite get us to that 0.5 value that we expect through pure dimensional analysis. But there are a lot of things that could contribute to this fact. First of all, we have a finite number of points, and that's really going to skew how well this represents the actual physical system of that spring. If the number of points were infinite, then the fit would probably be closer to what we would expect, that 0.5 factor. Another factor that might play into it is the finite time step that VPython uses in each iteration. This could also be a root of some uncertainty in our measurement. Furthermore, we can't actually know that that dimensionally analyzed relationship is what we actually want for this system. An experimental analysis of the system would have to be carried out dancing alone in regions at night. Dancing alone in regions at night. Dancing alone in regions. Dancing alone in regions at night. I need to go find some friends.